Thanks. So for those of you who don't know, I was in a little bit of a car accident a few months ago, and I usually run all over the place when I'm talking, but I'm going to sit down occasionally because I'm having some back problems from that. So I apologize. I actually had a bunch of pictures in my talk that I decided not to show from the accident because kind of, you know, but anyway, I'm going to talk about sensors and actuators and things, and so part of the reason why I think sensors and actuators matter is because it did things like saved my life a few months ago. True story. But in any event, so I sit at the University of Washington. I'm a professor on the faculty there, but I'm also an Intel exec. And what I do for these few years is to run our Center on Pervasive Computing. And our mission is towards pervasive assistance. And what that means is wherever you are, whatever you're doing, these days, there's a sensor nearby, there's compute nearby, there's communications nearby, possibly in your pocket, possibly in the vehicle you're driving in, possibly in the walls, in the factory, in the home, whatever. And we're about taking all those things together, using actuators and whatever data we have to help you go do a thing, whatever it is. It can help you with your health, it can help you with a task you're doing, and so forth. And that's kind of what we're about, and I'll talk more about that as we go along. By the way, I like to be interactive. Questions, raise your hand, yell out while we're going on. So if you have any thoughts. Kong, I know you'll have a question somewhere along the way. Go for it. You know. So what we're going to talk about. So kind of we'll go over can you guys hear me okay? Is the mics okay and everything? All right. So we're going to talk about how this center fits in Intel, go over the people. You'll see we have about 15 faculty plus some Intel folks. We'll talk about our mission, our approach, kind of overview of the research, and then we'll pick out a bunch of interesting research highlights. And there's lots of others I could have shown. They asked me for the webcast to not do a bunch of videos. I have a bunch of videos. If there's a part where we're going through and you guys really like the sound of the video, I'll jump over to it, but it won't show well on the webcast. So, and then we'll kind of wrap up. So in 2011-12, Intel set up a bunch of centers around the world. 7 in the United States and about another half dozen around the world in different topics. 5 of those centers are still going in the US. They are these 5 at these 5 schools. By the way, for those of you who know about social computing, it just moved from UC Irvine to Georgia Tech, so that's why if those of you know who happen to know about that center. And we just got renewed. These centers were for 3 to 5 years, 3 years nominally, and then up to a 2-year renewal period. We just got renewed, so we'll be going through about the end of 2016. So again, I mentioned our mission is towards pervasive assistance. So if you think about, just a question, how many of you have smartphones in your pocket or in your backpack or purse or whatever? Okay. So typically in your pocket, that means there's something on the order of 8 to 10 sensors, depending on how many cameras you have and all that sitting in your pocket. We all have them. Those, in this room right now, there's a bunch of sensors. On the roads we drive in, there's sensors. The vehicles we drive in. Think about how many sensors and actuators there are in a car these days. When we're in the accident a few months ago, all these airbags went off and all this stuff happened, and those things all happen like that and help not only save our life, but it's there's a lot of things you can do with it. You could have sensors that tell you the temperature if you need to know that. If a fire's starting, that we know. If something happened with your body, we're all going to be having stuff built into our clothes in the near future. So again, we're going to help you with whatever it is you want to do. And the method we're using for that, and notice the little play on words here, pervasive assistance via pervasive assistance, is we're creating some experiences and stitching together our sensing technologies, our understanding technology, which is largely AI, and turning analytics and machine learning and so forth, turning those things into interesting stuff, and then assisting people to do things specifically. So what does this mean exactly? So I'm an Intel guy. We love stack pictures. This is a stack picture. So starting from the bottom is sort of closer to the hardware and stuff, and up at the top is where the humans are doing things. And so let's start kind of at the bottom. So we do a bunch of interesting sensing stuff. And I'll talk more about each of these buckets in a little bit. But we do things around perpetual sensing. What would you think we mean by perpetual sensing?
Continuously sensing over a period of time.
So sensing over a period of time. So what's the problem with sensing over a large period of time? Imagine that there were sensors embedded in all these walls and out in the streets and all that. Well, tell me a problem with that.
Device life?
Yeah, so device life is one, but it turns out that if you have to have batteries where all of those sensors are, all of a sudden you now have a problem that somebody's got to replace those batteries every so often or whatever. And so we do a bunch of work in doing things without batteries. So batteryless sensing, harvesting energy and so forth. We'll talk more about that in a bit. Novel activity sensing, physiological sensing. Think of how many things close to your body where you can get all kinds of interesting things. Those of you who are interested in medical or biological stuff, right? I mean, whether it's a device you wear on your wrist, something around your collar, glasses you wear, Google Glass type style stuff, right? All of those things are touching parts of your body where you can get information. And we tend to, our center worries about non-intrusive kinds of things, although there are plenty of folks out there working on more intrusive kinds of sensing as well. And then we do a bunch of stuff with vision technologies, which we'll talk about more in a bit. So then there's a whole set of understanding, AI types of technologies, understanding human state and activities. And again, we'll talk more about what this means in a little bit, but a lot of activity and object recognition, and a lot of ways of taking sensors of different kinds and throwing them together to do something interesting. So let me throw a sensing problem at you. So imagine for a moment that you want to help people with medical stuff, their health and well-being. So one of the hardest problems in health and well-being stuff is figuring out what people eat. So how would you figure out think of what you ate today. So take, whatever you ate today, whatever situation you were in, candy bar from a machine, your breakfast at home, whatever it was. How would a system figure out what you ate? Think of the sensing problems that are in that. So what's hard about that? Brian, what's hard about that?
So it's
Uh-oh.
You don't have electronic composition on a lot of these sort of touch points, right? So the candy bar machine I can probably get pretty cheaply because the vending machine can probably tell me what I bought. But the apple that I ate for breakfast, I would probably have to visually recognize or using some other mechanism.
I'm trying to move to avoid the feedback. That's why I'm zipping around. Sorry. So there's a visual thing. So maybe it'd be a visual recognition, right? It turns out that it's not only hard because that means you have to have a system that's always watching, all right? But there's other things you can do. For example, if I know your location, right? Say, for example, it was around noon today. Where did you have lunch, Brian?
In one of the conference rooms.
Okay, so all right, so conference room. But let's say today you had gone out for Mexican food, right? Or
Not in our
Not never. Oh, sorry. What's good? What's good these days? You went to Zingerman's, okay? You're in Zingerman's. It's around noon. Chances are some percentage chance. So also you're mapping your location information. There's another sensor that our guys have been using. They've been taking audio and listening, and it turns out the most important thing about first of all figuring out what people are eating is first detecting that there's an eating moment going on because you're not eating hopefully 24 hours a day. So it turns out that there are sounds associated with eating. Clinking glasses, whatever, also chewing sounds and so forth. And so they actually did a little test with having a wrist-worn audio sensor. And it turns out they got between 85 and 90% recognition of an eating event. I thought that was pretty good. And so once you know there's an eating event, then you can start figuring out, okay, you were at Zingerman's, and it turns out on your credit card, because it's another piece of data, you allowed, and it turns out I see the tuna surprise sandwich or whatever on there, on your order. And then later on, we give you a chance to look at it, and you say, oh, it turns out that you and Marios went to lunch together, and you got tuna surprise, and he got a turkey thing, and you split them both, and you each had half. So you fix it, later on. So they call that semi-automated journaling. Anyway, but there's some really hard sensing problems like that, where you have a lot of different sensors, and you can figure stuff out. We'll talk more about that. There's also this notion, this is Gregory Abel's stuff. He talks about the 4 R's. And this is the notion of being able to, figure out what you have, how much did I use of something, being able to recall what's happened in the past to you over either short or long period of time. Resuming, have you ever made anything, built anything, added, cook something, right? You forget how many cups of sugar, how many cups of flour, all that kind of stuff. In complex environments like our smart wet lab, figuring out exactly where you were in a process and you stopped in the middle, right? How do you resume and all that? And then reflecting back on, you know, what's interesting and different. And then our two major thrusts through this work, these two capstone experiences. One is a smart wet lab, and I'll tell you more about that in a bit. So the biology lab, how you do repeatable science in the biology lab. We're doing something in a factory with that. But the important thing is it's a place where a smart task space, where you have a space where you're doing a thing. You're cooking something, making something, building something, and we can heavily sense that environment. And there's a task space that you do something. And the other is sort of more in the wild, helping people with their personal health. And we'll talk more about that in a bit. So, oh, sorry. Okay. So, you know, we've won lots of awards, sort of in 3 or 4 big areas. This notion of battery-free, you know, energy harvesting and so forth. And again, you heard me talk earlier about why that's important. Does that make sense, though, that, you know, there's going to be sensors everywhere? There's actually this idea that not only are there sensors that you can harvest energy from the environment and so forth, but you can actually seed the environment with energy so that you can grab power, grab sensing and do something. So for example, you could, in all those light bulbs around a building, around an environment, you could have power basically being projected out of those light bulbs so that you could have sensors doing something interesting in the environment. It could be a factory floor, it could be an office and so forth. Does that make sense? You can so in other words, you don't have to have batteries on in the sensors. They can just pull power off. They can harvest energy, you know, electromagnetic energy, for example, from the environment. And so you can seed power. That's a really interesting notion, especially in a controlled environment like a building, a factory, and so forth. And we've won a bunch of Best Paper awards. A guy named Josh Smith at UW is kind of the guy there. Some novel sensing stuff. I'll talk more about this in a bit, but some folks at one of the guys at UW, Shyam Golakota, has done this thing. Have you guys heard about this work? It's called YC. This is the ability to, so you're, we are basically giant bags of water, okay? And so any RF signal, every RF signal that's going around in this room right now, it's different because we're in this room. And so you not only detect that humans are here, but if you're focused on the right human, you can actually detect certain large gestures. So he's done this whole body of work where, and they do that, you know, using the Doppler shift. Remember the Doppler shift? So if I'm, you know, if all the different Wi-Fi signals going around here, he can detect like this motion. So you could, for example, be in your living room and want to control something, be in your office and want to do something, and you do a large motion, and so that's pretty cool. So you're turning RF into a sensor. There's a bunch of other things like this as well. And then algorithms, we have amongst the best algorithms in the world for various things. I'll talk more about that in a bit. But one I want to point out to you is those of you, how many machine learning people do we have in the room? A few, okay. So there's a body of work called hierarchical matching pursuit algorithms, or feature learning particularly. And the guys that did that were in our center. And those are all these benchmarks were set by that set of work. We've got lots of stuff in the popular press, lots of awards. Next week, the week after next is Ubicomp. And the Ubicomp 10-year Achievement Award was given to Dieter Fox, my co-PI, and Henry Kautz last year, and there's a bunch of awards like that. This is actually a pretty interesting picture. So the way these centers are set up, we're at 5 universities plus Intel Labs folks. And my partner in crime, Anthony Lamarca, and I are embedded on campus. So we sit at the University of Washington with the bulk of our faculty. We have folks like Fei Li, who probably a lot of you know from around here, because Fei's husband, Silvio, was here for a number of years. And Fei is now the director of the Stanford AI Center. Gregory Abel, well-known guy in Ubiquitous Computing. Done a bunch of interesting work. Tanzim Chaudhry. Tanzim's, one of her claims to fame is she does all this emotion and stress sensing. So for example, she can listen to you speak on your smartphone and know that you're under stress. Perhaps she could listen to my voice right now and say, oh, he's stressed out. You know? Henry Kautz, another AI person, past president of AAAI. And our bulk of our faculty are at UW. Just from Dieter Fox, co-PI, he's vision and robotics guy. Luke Zettelmoyer, natural language. Jeff Bilms, well-known machine learning person. Fogarty in HCI. I want to point out Shwedig Patel down here in the corner here. Shwedig is a MacArthur winner and has done some fascinating work around the combination of sensing and machine learning together. And for example, Schwettig's got some stuff where he can put one sensor in a home or on the electrical system, be able to tell everything that's going on in the home by looking at the signature of the electrical changes in the environment with one sensor. Same thing with the water system, identical kind of stuff. Fascinating thing if you want to know, I don't know, if your elderly mother's living in the house and you want to make sure that, you know, you see change in the coffee pot turn on in the kitchen and some water run in the kitchen, you probably have an idea that she's doing okay in making coffee or tea or whatever. 3 folks in color, by the way, are new additions to the center. A few folks have moved out of the center, Deb Restron and Yoshi and David Weatherall. But the additions, Shaim Golakota is the guy with the Wi-Fi gesture stuff I mentioned earlier. Eric Clavins is a synthetic biologist. He's the smart wet lab guy, and I'll tell you more about him in a bit. And Julie Kientz runs our personal health efforts. So now we're going to jump into, from that big stack picture, I'm going to jump into various pieces of work. I'm going to talk about kind of from the top down. So I'm going to talk about our 2 major assistants and what they do. So I want you to read the thing in the yellow box for a moment. So I don't know if that strikes you as frightening, but it does to me. What this means is that when biologists do work, they have a lot of trouble repeating something. Now, I thought it was hard for us computer scientists to...
That sounds great. It means we're not all that bad.
Yeah, right. But so the problem is that they can't reproduce their science. So why do you think that is? Nancy, what do you think? Why?
They don't have the right control structure.
Like,
The experiment.
right controls, okay. Yeah.
Insufficiently detailed descriptions of the methods.
Yeah, so I don't know if you caught that, but insufficiently detailed descriptions of the methods. And in fact, the person standing, that's a postdoc. I don't know if any of you postdocs or no postdocs, but what do postdocs usually do in about 2 years? They disappear, exactly. So the postdoc, say this postdoc from UW is now at Johns Hopkins being a professor. So when he left, all the experiments that he was the guy that knew how to do everything, he had the tribal knowledge, all that detailed description, he knew that you had to spit on it and rub it, you know, to get it to work, right? It's like my grandmother when she used to make, you know, recipes, she always put a dash of vodka in, took a sip and put a dash in, you know, and we could never figure out why our stuff didn't taste like grandma's stuff, you know. But that's a lot of that. The other thing you'll notice is, look, tell me about his hands. Look at his hands. Can you see his hands? They're in gloves, right? So it's tough for him to do things on a computer, even write things down. He's got a few little notes there and stuff. What he uses is actually a lab notebook, okay? So probably a half hour, 45 minutes after he's done with the procedure, he writes stuff down. So he probably says, I did procedure ABC 9 times, or, you know, steps 1 through 20, whatever, right? So there's a lot of other reasons, but you know, some of it's the tribal knowledge, some of it's the, you know, detailed descriptions. So some of the things we're doing is trying to help folks. We are censoring the heck out of that environment. So remember, that's a pretty complex lab environment that you've got there. Notice all the different moving parts. You know, he's pipetting little bits of stuff into, you know, other little bits of stuff, pouring colorless liquids into another colorless liquid. He's taking things out of freezers and refrigerators, putting things in petri dishes. You know, he's doing all those kinds of, you know, messy real-world things. And by the way, factories of certain kinds don't have similar kinds of characteristics. Factories, kitchens, you know, anything where you're repairing a motorcycle engine, doesn't matter. When you're doing a thing, there's always this messy real-world stuff that you can't get all the detailed descriptions. Why do some people who are repairing things are better at it than other folks? You'd have to follow them around and figure out exactly what they're doing. And in fact, in our fab environments, in our factories, we do that. There are some technicians who will go around in a factory and they'll do maintenance on equipment. And you take 10 different technicians and 1 or 2 of them will do things and their stuff will work 97% of the time. And the other 8, it only works 70% of the time. Why is that? Well, what they do is they follow people around and they figure out what. So for example, in that particular case, there's a technician in one of our fabs that the machines always work when they're done doing maintenance. And it turns out they have taken everything this technician does and they've made it the best known method, the rule. Okay? So these are the kind of things you can do. So if that person wipes counterclockwise, you know, or clockwise 17 times, that's what you do now. They don't know why it works, but that's what they do, you know. The other thing about, a couple other stories about this lab. So there are things that happen in this lab and people have no idea why something works or doesn't work. So there was a time in this laboratory where all the biology and chemistry labs stopped working for about a week. And I wondered, so tell me, somebody maybe guess why that would be? So it's a biology lab, right? So what do you think?
The wrong enzymes or something.
Wrong enzymes, okay.
Acids.
What's that?
Some acid spilled.
Something spilled? Is that what you said? Okay. Okay. Okay.
Something went wrong with HVAC.
Something wrong with HVAC, so the air supply maybe, or the heating or cooling, okay. How about the water supply? So sterile water, not sterile water, okay. Yeah, could be. Yeah?
You could have a maintenance man that got a cold and went around all the labs.
So a contamination of some kind, yeah, sure, somebody sneezed in the wrong place, yeah. Those are all great answers. None of them are quite right. Another guess? Okay, so it turned out they finally tracked it back, and after they're done with all these things, they clean them. They clean all the glassware, they clean all that. They have these industrial dishwasher type deals there. And it turns out that the person who manages the lab had gone out and bought a different kind of detergent, you know, for the dishwashers. And so what happened was, in some sense, it changed the chemistry or biology of the laboratory. And they immediately went out and bought the old kind, and things went back the way they were. Okay, I got a similar story about Intel fabs. So in the early days of Intel, so Intel was founded in '68. So in the early days, you know, first few years of Intel's existence, they were having problems in the Intel fabs, in this one fab. I think it was like every Thursday. It was a particular day of the week they were having problems. In the afternoons, Thursday afternoons, they had a problem. They had excursions in the fab, you know, issues in the fab. And again, so why do you think that might be? This is, you know, early days of semiconductor production, you know, it's like 1970-ish. What do you think it might have been? Yeah?
Is this your inbound logistics checking problem?
No, but maybe, I don't know.
The guy was individually counting wafers, and it's not that story.
No, it's not that story. Yeah, you hand here somewhere. Okay, so it turned out that the menus in the cafeteria were kind of relatively constant. And Thursdays, whatever day it was the day they served French fries. And so contaminants were coming back in on the people, you know, the oil and the salt and all that sort of stuff, and we're getting into the wafers and screwing things up. So knowing what's going on in your environment, you know, you can really tell. Okay, anyway, but there's, you know, interesting stuff. Okay, so we're using machine learning and task modeling, document task execution, recognize errors, suggest remedies. We're doing a lot of training here. That's actually a picture of the lab notebook. I don't know if you can see, but that's the real documentation process. So we're going and making this through, you know. So now we're documenting this with a ton of sensors. We have 6 or 7 cameras on the lab bench. We have various times we're having people use you know, various kinds of first-person, you know, egocentric vision type things, being able to merge those things together. One of the vision things, one of the videos I took out of here was, so Jim Ray at Georgia Tech is working on tracking gaze and being able to tell where your eyeballs are looking. So just when you're working on something, when you're working on some physical thing, where do you tend to look? Where your hands are, exactly. If you're, you know, you're fussing with something, you're doing something, you know, you tend, and where do you tend to look? You know, the next few seconds, you tend to look at what you're going to do next. So if I'm going to take this and pour it over here, I tend to look, you know, look here and then here. Experts tend to look slightly differently than novices, right? So Jim is doing all this great stuff about first-person vision and how it factors into the, you know, environments like this. But merging all these different kinds of sensing together, we are sensing everything in there. There's tags on almost everything in the laboratory. So every beaker, if this was a beaker, wouldn't say Coke on it, but, you know, or Diet Coke on it. So if this was a beaker, so think about what's the state of that beaker? Okay, well, There's the stuff in it. All right, so what's the temperature of the stuff in it? What's the composition of stuff in it? How did it come to be that way? Maybe it's been out of, one of the problems with an experiment could be it's been out of the fridge too long, so it's too warm, or some component was too warm. In step 3 of a 139-step procedure, it turns out you left something out of the fridge too long and it went bad. So now we could tell you on you're about to start step 4, you might as well, you know what, scrap this and start over because this whole procedure is not going to work, right? The other thing about this beaker, if it's a biology thing, everything that's ever been in that beaker, every state that beaker's ever been in the past might matter. If there's something that was in this beaker in a biology experiment from months ago, and maybe you can't use it for this thing you're using it for now. You have to scrap it or throw it away or use it for something else. Let's see. Oh, everything in the lab is sensed. So the refrigerator door opens and closes, the centrifuge gets turned on. I mean, all the different things in the lab. And the wet lab is a joint project across, even though the lab is at UW, we have folks working on it from 4 of our universities and the Intel labs as well. And basically, this is sort of the flow of what we're up to. We have a bunch of large data sets. If anybody here in vision, folks? Any vision people in here at all? Because there's data sets that you can get to if you want to see, because there's some absolute world-class data sets. And the interesting thing is, these people, there are hundreds of students going through the lab and they have bioengineering lab actually running in this classroom environment. And we're capturing, with their permission, so we have these huge data sets. And we're learning a bunch of things. And if you're a vision person, different kinds of vision stuff, that's putting those 7 cameras together, they're depth cameras, being able to put them together into a single point cloud, that's an interesting piece of work. So there's a bunch of stuff. We're actually, as I mentioned, we're moving this into one of the Intel fabs, and I can talk about that more if you're a manufacturing person and you care. All right, so now I'm switching to the other. Is there any questions on sort of the wet lab and how it relates to things people really do? Okay, so now continue with assisting. We're looking at the personal health stuff, and the notion here is that there's lots of personal health things. I don't know. Are any of you involved in personal health startups or anything? I mean, there's just things going on all over the place. But what we're really interested in is creating a self-experimentation environment for folks. That is, that to help you with your personal health and wellness, we've done experimentation in a bunch of slices. Like some of our, Julie Keynes has done work in sleep. Activity's easy these days. I mean, you can pick that up from, anyone. In my wife's phone has a great app. You can use Fitbit, whatever. Nutrition is the hard one. I think nutrition and emotion are probably the hardest ones. We talked about the nutrition stuff, the emotional state, there's stress sensing, but look up Tanzim Chaudhry's work if you're interested in sort of sensing emotion at Cornell. And she's got some interesting work, as I mentioned. So here's the stack picture for personal health, some of the things going on. So we want people to be able to recall what's happened in their environment. So if you gain 10 pounds, or you're having migraine headaches, or you're having irritable bowel problems or whatever, be able to recall what your situation was, what the air quality was where you were, what all kinds of things about you and about your activities the last few weeks. And we do a lot of stuff of putting together sensors at various levels, just like sensor fusion I mentioned before in the Smart Wet Lab. We do similar things for the personal health. We are not inventing a lot of biological sensors, typically reusing sensors in interesting ways. Now I'm going to tell you a few little cuts through this work. So there's a lot of different pieces to this work, a lot of different results here. But here's one piece from Kai this year. There was sort of the Quantified Self movement. We did a big study of the Quantified Self movement. It was a very well-received paper at Kai. And you can check that. It's one of Julie Keynes' students. So I won't ask you the questions because you can see the answers down here. But here are the typical things that the quantified. How many are you? Any quantified selfers in here? Okay. You guys know about this movement? So you do, Nancy. So all right. So you want to explain the way you think of it?
Well, it's sort of maybe my statement at the official way, but it's the Internet of Things applied to your own health and wellness.
Okay, so the Internet of Things applied to your own health and wellness. So there are people who write down or track everything about themselves. I mean, when I'm not hurt, I'm a runner, and I do keep pretty close track of my running and stuff. But not only people tracking their activity, but sometimes people track everything they ate. And I mean, there are students, some of the folks who are involved in this are students, not surprisingly. And there was a student in the study, and it's online, you can see it, but they tracked everything they ate and everything, just everything in their life, and then they tracked how well they did on exams. And this person, I think they were math, engineering, but something in the sciences, but they did better, they claimed, they did better on math exams after they ate butter. Now, you know, I don't know if it was true or not, but you know, there's causation and correlation, and they drew a causation, you know, result there, and I think maybe it was just a correlation, but I don't know. Eating detection, we talked about this a bit, but if you want to find out more about this, you know, Google Gregory Abel's work or Edison Tomas, his graduate student. So we're helping build a sort of a whole environment around self-experimentation, allowing people to sort of run experiments. And the interesting thing is when you have an issue that you want to explore, you know, migraines, irritable bowel, you know, anything that's going on, you want to know what the triggers are. You have a food allergy. Let me give you an example. So typically, I don't know, have anybody ever done like an elimination diet to figure out a food allergy for either you or your kids or something? So what happens? It takes weeks and months to you know, to figure out, you know, you start with like rice. Okay, rice doesn't bother me. Okay, boiled chicken, you know, whatever it is. And then at some point, you know, 3 months later, you get to the fact that you're allergic to strawberries or something, right? So it turns out they have some methods where they're using some randomization techniques, some statistical techniques to be able to put together a more intelligent approach with a gastroenterologist, experimental design folks, people in the iSchool and the Human-Centered Design Department, computer scientists, together. So maybe you can do that same thing in a week. You know, so it's both the technology side and also the statistics. And then, you know, and the medical side as well. And so this could be a very interesting result for folks. So you don't have to do that stupid elimination diet thing that some of us have done. And there are a bunch of physiological things as well. Okay, jumping to human state and understanding human state and activity. This is basically algorithms. For those of you who are algorithm folks, so some quick stuff. So I mentioned the ability to understand the combinations of different things. And I'll talk more about this work in a bit, but there's a guy named Jeff Bilms who's in our center who, for those of you who are machine learning people, he wins a lot of machine learning best paper awards and such. And he's got some very interesting stuff. Dieter Fox and his students are doing very fine-grained activity tracking. So there are models for like how the hand, you know, the hand works. There's people well understood about, you know, tracking hands and stuff. As soon as I do this, all those models get thrown out the window. It's very hard when you have, you know, occlusion and all of that kind of stuff and figuring out what the hand's doing and what's the hand, what's the object. You know, in a place like our wet lab where you're picking up things, putting things down. So Dieter and his student Tanner Schmidt have put together a model. Not only works for hands, but also for bodies. Any, I forget the articulated, you know, body, whether it's a hand, a robot. So it's useful in robotics. So it's a pretty general result. And if you're vision folks, you take a look at what he's done. This tools for task debugging is kind of cool. They're actually doing debugging of physical tasks. So think of it as debugging physical tasks, which is kind of an interesting approach. So Fogarty's an HCI person, so working in the wet labs, giving him a chance to check that out. All right. So this is a little bit of dives on a couple of these things. So this is Bilm's work. If you want to take a look at Jeff's work, so he's done a kit called GMTK, which those of you who want stuff like this can go download it and take a look at it. And you know, again, I don't know if it interests you, but it's using deep neural networks to go. And he has this notion called subfunction optimization, submodular optimization, that supposedly, you know, it allows a lot of these things to scale in beautiful ways. I don't understand the math, but go look up Jeff's stuff if you're interested in that stuff. Remember I mentioned being able to track gaze and all that? This is some of that work from, and they also have not only taken being able to track gaze, be able to predict it as well. Okay, so to be able to predict where you're going to look, and at some point you don't even need to do the gaze detection because you get good enough at predicting where people will tend to look during certain procedures and things like that. Oh, this is the hierarchical matching pursuit stuff. Best algorithms in the world for feature learning. And it was done originally by Li-Feng Bo, who's now at Amazon, was part of our team, but he and Dieter and some Dieter students. And we've taken this stuff at Intel and done a bunch of great things with it. These are very powerful algorithms. They're setting all the benchmarks. And if you want, get availability of that, I can get you that code base. Okay, so Josh Smith's work, and battery-free sensing. One of the recent papers they did was, so one of the hard things in any power harvester that's pulling RF signals, stealing RF, stealing energy out of the air, is that typically you go at a particular frequency. And it turns out that Josh has built up the first multi-band harvester that's really shown some really wonderful results. It was best paper at RFID. And there's a bunch of stuff. Check out Josh's work if you like this, if this stuff interests you. And the other big technique that they've been using to sort of steal power, reuse power, is backscatter. So you guys know how RFID works, right? You shoot power at a passive antenna and it just bounces back, and that's so the antenna has no power at all, and it's just sending back. It's what an RFID tag is, right? But you can do similar things where you can bounce power from one device to another that are all unpowered. So an environment of sensors, and you can do things like, for example, so Josh has this little experiment he shows where he can take and move money, from one device to another. So be able to shoot power at one device, it bounces to another, and so you could actually have communication going on between devices without any power within those devices, as long as you have it in the environment. And they have some pretty nice results here. Novel activity sensing. I'm going to mention a couple different things here. The home as a sensor, I mentioned Shweta Patel's work. But if you're interested in that sort of stuff at all, this is some of the stuff that won him the MacArthur Award. It's fascinating work. Mentioned this thing about smartphones. Using RF as a sensor. This is the Wi-Fi gesture stuff. And I have a really nice, there's a nice video at that link on YouTube. And I think I'll wait till the question period, and if you guys want to see it, if we get done with the questions, I can jump to it. But it's essentially, they can detect 8 or 9 different kinds of gestures. In the demos I've seen, there's 2 or 3 of the gestures really work well. Because again, Doppler shift, right? Moving towards the antenna, the collector, moving away from the antenna. Those things are pretty good. The other ones, aren't quite as good. But the point is, be able to turn RF into a sensor, a new kind of sensor, I think is a pretty cool idea. All right, so I'm going to kind of wrap up. So we have this center. It has a bunch of different folks in it who do lots of different things. It's very interdisciplinary, right? There's advances being made in HCI, there's advances being made in AI, and it's across a bunch of universities. We're iteratively prototyping. We have a couple of major applications that are pulling things together. And in doing these things, by the way, those applications, they have real customers, people doing real world work. I mean no offense to anybody who's a robotics or vision person in the audience, but I've seen some great robotics demos on video, and then I've gone to the labs, and I walk in there, and it turns out the one time they got it to work, they've had it on video, right? I mean, think about all those towel folding demos you've seen, and all the rope tying demos you've seen, all those things, right? Those are really hard in real life. And it's similarly with vision. A lot of times you can get it to work sometimes, but not others. But getting it to work at a level where there's where the students using a lab or whatever, that's a harder deal. And this was our little stack picture, which kind of focused all around. But I want to make a couple of observations on the center. So first, this notion that we're having a guiding, okay, maybe you all realize this, maybe you don't, but a lot of the professors I know tend to work as a professor doing a thing, right? And occasionally they have one collaborator or something. But to get a group of professors collaborating on one central thing is an unusual thing for professors to do. It's not the natural thing. And sometimes the NSF does it through things, and the NIH. But I think we've accomplished that through these capstones. So algorithms, sensing, being put together in interesting ways to be able to go do this smart wet lab thing. So that's kind of working. I think embedding folks into the university, like industry folks, on the university campus. I think it sort of works. If you can get the right people to come to campus and hang out at least half time or something like that. I'm there about 3/4 to 80% time, and Anthony pretty much there 100% time. Plus, but there's some things there. I happen to have been in Intel for 20 plus years. I had all the experience of running labs, and so bringing technology into products. And so that's what I do. A lot of my time is I connect up, industry things with, the academic. I have a foot in both camps. Some of our centers don't work quite as well. They don't have the right people, for one reason or another. But I think if you have the right folks, this actually can work pretty well. Another observation. I think the battery-free thing is really a very powerful idea. I like this idea of seeding the environment with power. I mean, think about how many opportunities that opens up. You can sense, you can communicate, you can compute with no local power. If you can build an environment like that, you can build industrial environments that work that way, this room, for example. So I think it's a very powerful opportunity. And something I didn't put in the talk, but is important to realize, it's sort of a different, I forget the name of the law, but a corollary to Moore's law about power, that the amount of power to do a particular amount of compute, sort of, the amount of power you need kind of goes down over time per amount of compute. And Josh has some nice curves on this. But if you think about that, that means that you're getting more and more capable over time for less and less power. And at some point, you cross some thresholds where you're able to do something by harvesting some power and going and doing something interesting. So that's kind of a fun thing. And then you can almost use anything as a sensor. It turns out these smartphones, I mean, think of all the different applications we all have on our smartphones where they're using the smartphone, the sensors in different ways. So my phone's down here, but I have one of the things Schwettig's also built in his lab is a grip sensor for the smartphone. So here, give me your phone for a second. I think it's pretty weird but they can actually detect, when you grip your phone, you squeeze it or tap it, right? There's no grip sensor on your phone. How do they do it? Well, they use the gyros and the accelerometers, right? And they get a signature. It's machine learning, right? They just learn what a grip looks like. And you can see why if you look at the phone, it's moving a little bit when I grip it, right? So you can, this Wi-Fi gesture stuff, the ability to turn your whole house or environment into a sensor, like Schwettig's done with the electrical and the water system. Think of all the places where our bodies get touched by health stuff. All the clothes we wear, everything. All of these things have opportunity to be sensors. And then, of course, you add some compute and communications that you can do wonderful things. And with that, I'll quit and open up for more questions. Oh, question right here. Yeah.
Hundreds and hundreds of people. And I really been telling everyone, you should stop what you're doing and come join my dream or join this thing, because I think it's better for you economically.